And here we have Dipankar here. So he's a data advocate at Dremio, and he's also the co-author for Apache Iceberg, the definitive guide. And so now I'll just pass the ball to Dipankar to start with his presentation.
Yeah, thank you so much, Simran, for the quick intro. Yeah, I'll get started, so that we don't waste any time. Today we're going to talk about a bit about data lakes and data lake table format. Specifically, our focus would be on Apache Iceberg. You might have possibly heard about it or read about it in the recent time. So there are a lot of momentum happening. But yeah, I'm here to demystify all of it. So I think hopefully this will be like a good learning experience as well. So a little bit about me. Currently, like I said, I'm a developer advocate or data advocate here at Dremio. Dremio is a data lakehouse platform, and we'll get a bit more into what lakehouses are in a moment. But yeah, I currently work on a lot of open source projects like full time, such as Iceberg, Apache Arrow, Nessie, etc. And my past has been in various roles in the world of engineering, like software engineering, data visualization, data science, and stuff. I'm also super excited about the book that I'm kind of co-authoring right now with other co-authors that you can see in the screen. So this is going to be the first book on Iceberg, so that's exciting, and you can pretty much look forward to it. So this is on early release program right now. So basically, O'Reilly has a program where you can basically write out the chapters as you're done, and you gather some realistic feedback from folks like you who are into this background and engineering part of the data. And that way we can make the book more robust. And I think we should have this book ready by end of this year or early next year sometime. Yeah. And you can pretty much find me every day on LinkedIn and Twitter. So even if I'm done with the session and you have some questions and you want to reach out to me, here's my LinkedIn scan, and I'm also available in Twitter as well. So in terms of the key takeaways from today's talk, we will start with how data architectures have evolved over these years, and then we will come into one of our prime topic, which is lakehouse architecture. And then we'll go into what Iceberg is and how it enables the lakehouse architecture. Like that's one of the main component of a lakehouse architecture. And then we'll go through some design benefits, and we'll end it with some high-level table format kind of comparison between the three kind of existing today's popular data lake table formats coming from the other Hive world. So let's get started. So over the years, organizations have been investing heavily on kind of building centralized, reliable, and scalable data platforms, right? I mean, the whole idea was that if they could democratize data, it would allow data consumers. So for me, consumers are like analysts or like data scientists who basically want to leverage the data and enable insights and reporting and prediction models around it. So data warehouse were kind of the first one that enabled to deal with this. Basically, you could gather data from a variety of sources and dump it into a warehouse and in a structured way. So you have a rigid structure in that. And you can basically use that structure and build up analytical tools and applications like BI reportings on top of that. And data warehouses, we pretty much are aware of it at this point of time. But data warehouses also lack certain abilities. So like things like dealing with unstructured data. Although right now, I mean, in today's cloud data warehouses, maybe there are some abilities. But again, there are some caveats as well. So for more advanced use cases such as machine learning and streaming, those can be a problem as well with data warehouses. So then came the era of data lakes. Actually, it started with the kind of Hadoop ecosystem, which was kind of like the on-premise data lake at that point of time. And data lakes were great. Organization could basically dump all of their data, whether it's structured, loosely structured, unstructured, in the data lake. Such as, for example, in the big data world, it was HDFS, right? The Hadoop file system. And then with the rise of cloud and its kind of cheap price and the ability to scale, resources as we want, we have the cloud data lake storages now with things like Amazon S3, Azure Blob, or Google Cloud Storage, all the major basically cloud vendors. So you can basically scale out storage as you would like, and try to build up your storage system as you like, and store as much data as you want. But there were a couple of problems in data lakes as well. So first is you can't just dump data and let consumers like analysts and scientists deal with the physical stored data, right? So if you wanted to do BI and reporting, you still need to organize the data and get it out in a structured form to a data warehouse, and then you could do additional reporting on top of that. So that is another caveat. So even though you had something like a data lake, basically you have to export a part of it, a chunk of it for your analysis and those kind of things. And the most important problem was that data lake, they lack those atomicity and consistency guarantees with transactions. So by transaction, I mean things like updates and deletes and even things like basic writes or reads. So you cannot do a ACID-based transaction on the data lake, and that's where the problem with concurrent writes happen. Someone is writing something in that particular table, something fails, or you end up seeing some bad data that impacts your production workloads and your reports and models and stuff. So that is something that we cannot afford in a data lake, and that's what was one of the main problem with data lake. Also, it was getting real hard to make sense of all of the data, right? Because there is no real governance or like data quality checks on the data that was dumped. So usually such data lakes are dubbed as data swamps. Eventually, we don't have that kind of maintenance and governance around it. How can we even build a like machine learning model if we're not sure of the quality of the data, right? Ultimately it's the data that matters. So or for example, how can the decision makers use a reporting dashboard to like derive insights if the data is kind of not legit, right? So this gave rise to a new architectural platform called Data Lakehouse, which is why we are here today. And you could probably guess it is in a way it's bringing the best of data warehouse and a data lake world. So now you can basically run any workload that you could in a data warehouse, and also take advantage of a data lake's abilities. So data warehouse has great data management features, but lakes are very scalable and agile. And with, like I said, with cloud like S3, they're extremely cheap as well. So so really the best of the both world you get with the lake house. So just to give a visual picture, I'm a person who kind of like to see things visually and kind of leaves a mental impression as well for me. So this is one of the things that I want kind of like to take away from this particular talk, is that there are a lot of technical components here that kind of involve together and forms a lakehouse architecture. I think it's important to note here is that not each of these components are tied to just one particular single system, like we had in the past with data warehouses and stuff. So now we have the ability to actually, mix and match things as we want, depending on our analytical requirements, right? So for example, like today you have BI, but in the future, as you mature analytical journey, you might want to like do some advanced, modeling and stuff. So you want to do bring another set of tools for doing that. So you really don't have to change anything to bring those tools. Ultimately, you're building upon this kind of, the foundation. So this is what the foundation looks like. So I'll start with I always start from like the bottom to like the top so that you get an idea of what we're talking about. So in the bottom part, we have the data lake or the data lake storage, which is where your data lands after ingestion from operational systems, right? So, you're doing some ETL or ELT and you're bringing the data and storing it into a data lake storage. So like I said, S3, Azure Blob, Google Cloud Storage, whatever cloud or whatever, it can be on-premise as well, like HDFS, right? So, you can basically land your data into this particular data lake storage, and that's where you store your data. You have the scalability and performance and security and stuff, most importantly, in the data. And a layer on top of that is the file format. This is where the actual data is basically stored, right? And written into a particular file format. It can be row-based, it can be columnar formats. Usually, we would like to use columnar format specifically when you're dealing with kind of larger amount of data, because it provides advantages with like compression and like reading or sharing data across multiple systems. So some of the common file formats like Parquet or are kind of really beneficial as well. But again, you're also not limited to that. You could also use CSV or JSON as well. So any kind of file format. Now, the most important component that makes up a lakehouse, like I said, is the table format. And that's a layer on top of the file format. So you have the storage, you have the files, and then you have the table format. And we will learn more about the table formats in our next slide. But more generically, what a table format does, it abstracts the physical data structure's complexity. And basically, it allows different engines to work simultaneously on the same data set, right? So we will, again, like I said, we'll get more into the next slide, but the Apache Iceberg, Hoodie, and Delta Lake are kind of the three most popular table formats right now that kind of have been operational in the new data lake kind of space after we moved from that big data and Hadoop and Hive world, right? So obviously, these are like not new things. Like like I said, in the past we have the Hive table format. So Hive came out of like Meta or Facebook at that point of time and basically led us to today's format like Iceberg. So I think that was also really instrumental in the development of today's file formats table formats as well. And then we have the compute engines, right? So compute engines or the query engines are basically the one that are crunching the data, right? So they are responsible for like processing the data and proving efficient read performances, doing things like transformation, aggregation, or distributing workload depending on if it's distributed analytical engine or not. So engines like Spark, Dremio, Sonar, Flink, Trino, Presto, there are a lot of compatibility. I have a slide basically that kind of gives you an idea of what you can use today with Iceberg. But again, that's there are a lot of adoption happening today. And the final component of a lakehouse obviously are the application basically that are interacting with the data, right? And these tools can be like BI tools, like I said, with Tableau, Power BI, or Hex, or notebook based tools like Jupyter Notebook, who basically using for like machine learning based framework like TensorFlow or PyTorch. So ultimately, the whole point is to make data analysts or data scientists life easy, to get real access to this data through these kind of interfaces like ODBC and JDBC or Aeroflight. But that's a different discussion, not for today. So moving on to really focusing on our like the middle layer, which is the open table format. So what is a table format, right? So usually with databases, we have seen the concept of table, right? It's not a new concept at all. Like companies such as Oracle, Microsoft, they have been doing it with relational databases for years, and we know and we understand what tables are. So basically, it is a way to organize a dataset's file to present them as a single table. So users don't really have to know about the physical bytes and file, and they can just have that abstraction on top of it, right? You don't need to worry about what's happening below. You just have a way to see, okay, these are my set of files. I'm organizing them as a table, and I'm presenting it to my query engine so that I can query my table. That's it, right? So in the big data world with Hadoop and HDFS, we ended up ultimately with the Hive kind of engine, right? So more people have access to data, but there is also a need to define a dataset schema, right? And how do you kind of refer to that dataset as a table? So engines can interact with it, right? So which gave rise to the Hive table format, right? So we have the Hive engine and we had the Hive table format for that. So Hive table format basically allowed democratization of data using something called Hive query language. I'm pretty sure a couple of you might have already used it in your past work or whatever. But HiveQL was similar to SQL, right? It was a way to basically abstract that and provide more users the ability to access the data, right? So with Hive, we have in the Hive table format, we have a table one in database one, as you can see in this image, and it's composed of one or more directories. So the concept here is in Hive table format, table is basically the directory, and inside the directory, you have the contents of the list of the files, right? So let's talk about this in some more details. So in the Hive table format, the table content is files in one or more directory. And it's important to understand that because we are going to like take a different approach from here when we're talking about Iceberg later. So here we can see obviously one in this image, but obviously at scale, this would be like a lot of directories. And basically the tracking is done at a folder level. So whatever is in their folder, the engine will kind of like go and open up each of the folder and read the files and read the data. And that's how it works. And pretty much this has been the de facto standard since the mass adoption of Hadoop, like I said. Facebook brought Hive for SQL on Hadoop. So basically you had like no need to write MapReduce JAWS, which is pretty like cumbersome. Basically democratize data and users and allow more people to use. So definitely being the de facto has some reasons behind it, right? And some advantages. We have obviously worked on the Hive table format, and we have realized about those advantages. So I'll go over a couple of them advantages, and then go back to like seeing what are the cons and how they can build up on top of that. So basically, first it works with every engine, and there was no other table formats to allow that until recently. So that was really great. You can use different engines with Hive table format. Secondly, it had more efficient access pattern, such as partitioning scheme and things like bucketing, so you don't have to do full table scan for every query, right? So that was super important as well. Also, they were file format agnostic, so you can use any file format that you want, whether it's Parquet, CSV, doesn't matter. So it was really good to have that kind of different file formats used with Hive. Next, you could atomically update a whole partition. So, for example, you can take a whole partition and you can change the data, whether you insert some record or delete something, and basically you write the data into a new partition, right? And when you're writing it, no one sees the changes, and then you atomically swap that reference in the meta store. And this is how the Hive meta store came into the picture, right? And basically allowed us to do things like atomic transaction with the ACID guarantees and stuff. And HMS, the Hive meta store, was basically a single answer, a central answer to what's in the table, right? Every engine that kind of used the Hive meta store got to know that the same result. They could see the same data set. Like again, there are certain disadvantages to like every technology. Something we always build up on existing technologies and stuff. So it also brought certain disadvantages. So first, the smaller updates were kind of inefficient. Because you only atomically update a whole partition. If you only want to change a few rows, and a lot of times, you can see how it can be very inefficient at times, right? And you had no way to change data in multiple partitions safely. So basically, those atomicity guarantees kind of lacked in those, if you had to change data in multiple partitions. So if you want to insert a row into different partition, you cannot possibly do that with those atomicity guarantees in Hive. That was one of the limitations. And the same thing with multiple jobs, right? Modifying the same data set. Although different engines could read data from the same data set, those guarantees were not really present with the Hive table format. And also in the Hive table format, like we saw, the files are under folder, right? But engines can only read files, right? They won't read the directories. So engines would take a really longer time to basically read by going under each of the directory and opening each of the file, reading the content and closing the file. And this only, you can imagine how things can be at scale, like when you have like a petabytes of data, for example, and a lot of directories and stuff. So your engine is going to be really lagged on that. And we'll deep dive more onto it on a use case by Netflix actually later, and how basically led to Iceberg. But yeah. And users have to know the physical layer of the table. One of the application of this is the partition. So in Hive, if you're partitioning your table by day, and your table has a data in its like timestamp format, right? For example, like year, month, date, and hour, minute, second, it will basically do a full table scan unless users explicitly mention the partition column in the query, because the engine doesn't really know like if there is a mapping between that, the timestamp translation and the date, right? So it would probably have to go to the physical partitioning scheme that is like 2022 slash this month like and slash this date. So you end up with really expensive scan, and at scale this would be a huge problem. And also you need to educate people, right, on the file system and stuff, and you need to like let them know that, hey, this is how you have to query the data, right? Which is like really tough. Last, the table stats, kind of the Hive statistics were often stale. The table stats in Hive are basically gathered in asynchronously mostly, so they might become out of date. Also, to collect these stats, you will have to run expensive read job. So realistically, they're hardly run. In my previous organization, they were hardly run. But table stats are very effective for query planning and pruning and stuff. So we would really like to take advantage of that. So these problems are pretty much common in every organization kind of at scale, and Netflix were kind of the main one to look at this problem. So they went to the drawing board, and they were thinking that instead of putting band-aid on each of these problem, can we take a step back and see the actual issue here, right? Because in a long term it's going to be difficult. Like, so they had some goals they wanted to achieve, and I'm going to just list out some of the goals. So one of the first goal was that they needed table correctness or consistency. Like that's important for any organization, to be honest. You want to be able to have your trust in data, to make those data driven decision. And every query that you run from a technical perspective, it should also return the same result. So that's super important. So the consistency and correctness. Next, faster query planning and execution. So one of the query, and I'm going to talk a bit more about it, but for one of the query for Netflix, they took 10 minutes just to plan that query for a week of data, and just for one metric. And users are not going to wait for that long, as the performance is really a key in this kind of thing. So that's another thing. Next, they didn't want to worry about the physical layer of the data. For example, with partitions, like I said, if you have to query using a date, you just should not have to worry about that particular thing, right? Can we just have the software or the technology to take care of that, right? Because users do not have to know about partition just to query simple, one day of data, for example. And there were a lot of problem with table evolution, and this is something we see usually, like tables grow over time. Businesses have different requirements, schema changes. We need to embrace that, and we should be able to be ready for that, right? And to accomplish all of these things, but at scale, we can take care of these things probably at a small scale and in a small data set. But what if I had a huge table with large amount of data, like petabytes and like gigabytes of data, and it only grows, right? For organizations, we are only, that's the whole point of having a data lake at the first place, that we want like more data. So when looking back on these kind of band-aids and intermediate solution and all these cons that we kind of went through, the way they could solve this was actually pretty simple. So the problem with Hive was that it was tracking the files at a folder level. So instead, let's track the file at the file level, right? And that's the core. That's the core basically. So you can really mitigate those kind of cons with this small change in the design of the table format. And this is where Iceberg comes into play and addresses these kind of problems. So just to recap what Iceberg is and isn't, it's always better to have that context before we deep dive more into the architecture, because we have seen that with Hive, right? Hive is quite nebulous. It can mean different things to different people. Some people think it's an engine, some people think it's table. So better to have that distinction beforehand. So what Iceberg is, it's a table format specification. It's a way to lay out the bytes in the form of tables, that abstraction layer on top of the file. It's a set of libraries and APIs basically for interaction with the specification. So any execution engine or compute engine that you bring, for example, Spark, they have to leverage these basically libraries, and they can do all the things that we want to do. It's not a storage engine, not an execution engine. Like people confuse sometimes whether it's like, okay, can I use Iceberg to process this data? Well, it's not really an execution engine or a compute engine. It's basically a table format for your data lake house or data lake management, right? So those are the things that you might want to have like an idea on your head, just so we move forward easily. So now let's deep dive into the Iceberg architecture. I think that's super important to understand the way Iceberg is like kind of built, because that's how you kind of like understand how you can solve this problem and realistically approach some problems in the production environment as well. So as you can see in the image here, this is a high-level architecture of Iceberg, and we will go from the top to bottom and try to understand the various components of Iceberg. And at the same time, we will also focus on what happens when we, like for example, do some read and writes and those kind of things. So we basically have three layers here. One is the catalog layer, as you can see on the top part, that particular kind of like database kind of thing. That's the catalog, and I'm going to talk more about it in the next slide. And then in the middle part, we have the metadata layer, which is actually like the core to Iceberg. This is how you kind of achieve all things like performances and advantages with statistics. You can basically deal with, you don't even need to touch data files at times. You can just use the metadata layer to like get information about a data lake health, for example, right? How is my data lake doing? Or do I have a lot of small number of files? How do I deal with those kind of thing? So metadata is really the core in Iceberg as well. And the third is the data layer, which is, like I said, it's like the raw data files, basically Parquet or org, or any kind of data files, for example. And the first thing here is the Iceberg catalog, like I said, right? So if a user is trying to either read or write data from a table, they first need to know where to go, right? And catalog is that place. So it's a place that kind of keeps that reference of the current state of the table. Okay, what is my current state of my table? What is the current set of records? So the concept is you can store as much data in a data lake like S3, right? But you need some kind of a locking mechanism for atomicity and consistency guarantees that we kind of talked about, and those downside that we saw with just having a data lake architecture, right? And most data lake, they don't provide those guarantees, right? So Iceberg catalog basically serves that purpose. It brings those atomicity and consistency guarantees to doing things like concurrent writes and reads and those kind of things. So it's super important to have a catalog in Iceberg architecture. So the catalog can be a lot of things, but like I said, the key requirement is that it must support that kind of atomic operation to update the pointer of the current metadata. Because every time we kind of, and we'll see that later in the slide, that every time we make kind of a write, the state of the table changes, right? And the catalog will keep a track of that particular change. And every time someone else comes to read the data, they always want to see the fresh set of records, and that's what is super important. There can be a lot of catalog options like HDFS, Hive Metastore as well, Nessie, Dremio Arctic, AWS Glue is pretty common. You can also build your own catalog now with the REST API, so that's something also super interesting if you want to delve more into catalogs. In terms of what it contains, let's go straight ahead. Like I mentioned, like it holds the name of the location of the current metadata file. So for what happens is, like for example, like if you basically, let's say you are doing like a select star, right? You are basically trying to like read a table from a like table db.table1, let's say. So you go to the catalog and basically ask, hey, can you give me the location of the current metadata file? And the catalog will give you the location. And that's how you always see the fresh set of record. So basically, as we go on our way, and since now we have the location of the current metadata file, as you can see here in this particular excerpt that I have put it up, that you can basically see like the snapshot ID and the manifest leads. So before I go to this part, one of the key things here to note is that the snapshot, right? So what is a snapshot, right? So snapshot is the state of a table at a given point of time. So like I said, any write operation that you do, like for example, like creating a table or inserting some record, or deleting some record, everything is captured as a snapshot in Iceberg. And that kind of helps Iceberg to keep a linear historical track, and allows you to do things like going back and reverting things. So for our select query, like let's say hypothetically we have issued a select query and we got the current metadata file from the catalog, that this is the one. And from that catalog, from the metadata file, we got the current snapshot ID. And based on that, we also got the manifest list, which is basically that you see over here, the next part of the component, right? So the manifest list is basically a list of the manifest files. Let me just go over here. So a manifest list is basically a list of the manifest file. It's basically kind of like an index that is keeping a track of all the manifest file. And within the manifest list, you can see information such as the manifest list file path, when it was added, partition specs, and those kind of important information that can help you with like things like partition pruning. So you don't really need to go to the actual data file. So now we have the manifest list from here and the set of manifest files. So, we get the manifest file path location here. And let's say hypothetically, this is the one right now. So, based on the path location, we'll go to the next part, which is our manifest file. So the manifest files basically gives us the list of the actual data files. So if you see the kind of like the relation, it started from here, went to here, then the manifest list, then the manifest file, and ultimately the manifest file is the one that's kind of keeping a track of all the data files, the Parquet and or all the the raw data that kind of landed in your data lake, right? So we will see things here such as the file path. As you can see here, the file path in the data lake, the format of the file path, the statistics, that's super important as well. The lower and upper bounds, for example, of a column, that can be super helpful again in terms of pruning and like avoiding scanning all the file, thereby making the query super faster. So at a leaf level, manifest will keep a track of all the data files. And for, let's say, for our select query, we will grab a file and return it back to the user. So this may seem like a lot, but this is way faster at runtime. I'm just breaking it down in terms of the architecture, so it kind of like remains like a kind of like a mental picture that, okay, these are the components involved, and this is how Iceberg kind of operates throughout it. So now that we understand the components that make up Iceberg table format, let us go through a couple of examples and see what happens when we kind of do like CRUD operations, right? For example, creating tables and updating tables and those kind of things. And that way we can basically see what's happening under the hood, and we can basically use that as a debugging options. Like, for example, in your work, if you adopt something like Iceberg, you might need to debug it like for some other reason, like, so that's super helpful as well. So let's first create a table and try to understand what happens underneath, right? That's the first step. Like, that's the first step you'd probably take when you like adopt something like Iceberg. So we will run this particular create table statement, and when we execute this statement, you will see on the right-hand side. So basically on the right-hand side, I will try to basically give you a diagrammatic flow of what happens with this particular components or layers that we talked about in the last slide. And on the left here, you can see this is the catalog, and this is my file system. This is my actual file system on my data lake. So as you can see here, when I particularly executed this particular command, right, we have 4 columns here. We have the order timestamp column, which we have partitioned by hour. And we will look more onto it, but you can see that it's partitioned by a reference. This is not a new column. Like in the Hive world, this would have been a different column, right? But here it's basically the same column. It's just a transformation on that particular column, right? So we created a table, and what happens is it adds a metadata file. As you can see here, it's a metadata file, right? And it has, in the metadata file, it will have the schema and the details, but we haven't really inserted any records at this point of time, so we don't see any actual data layer or the data file. Right. So as you can see in my data lake file location, I have the metadata file folder and the data folder. Inside the metadata folder, I have the version 1 of metadata, which is this one, and my data is not there because I haven't really inserted any data. So now let's say let's insert some record. We have this insert statement, and when we go and execute this statement, basically this is what happens with the Iceberg components, right? So the whole point here is 2 things to remember here when we are kind of writing data. The path that Iceberg takes is like bottom up, and when we're reading data, for example, select something, it's coming from the bottom down here. So whatever engine, let's say you use, let's say Spark to like insert this particular record, right? So it basically went on and wrote the first file in Parquet, and that's when it knew the info also about like from Parquet about the upper and lower bounds, and the null value counts and those kind of stuff, and it created a manifest file using those information. Right, and this is a manifest file that we talked about, where we can use this information to kind of do things like file pruning and stuff. And from that manifest file, it kind of like added it to the manifest list so that it can track all the manifest, and all the changes happening within it. And after that, it basically created a new metadata file, right? As you can see, this is the metadata file that we had from before, right? When we ran that kind of create table statement. And now we have a new metadata file, but it's important to note that basically we read the original metadata file and appended this new information with the new changes. So as you can see, in this metadata file, there was snapshot 0, but now we have a new snapshot, but we still keep a reference of the previous snapshot, right? And that's up to us. Like we can set to, we can decide how many snapshot we want to keep a reference to, and we can also decide to expire snapshot, because eventually your snapshot might be a lot on your data lake, which can impact your storage and stuff. So you might want to have some kind of maintenance strategies to kind of clear that off. So so now we have the kind of like this the current snapshot, which is the snapshot one, which is pointing to this manifest list. And after we kind of write this metadata file, the engine will basically update the catalog. And if you see the catalog, the pointer here, now it's version 2, right? Initially it was version 1. So in the file system, like, now we see the data file folder has a, it's partitioned by order timestamp. So we have a partition here, and we see the new parquet file, which is this file, and we have the manifest file, the manifest list, the version 2 metadata, which is this one, and it has been updated to be the latest one. So any other, for example, you now use like a Dremio to, like, query this particular table, it will still be able to read this particular newly inserted record, because all it has to do is go to the catalog and ask for the latest metadata file, and it can basically follow this particular path to get the data file result. So that's it. So this is how the insert work. And obviously, like, this is a pretty simple example, but again, at a larger scale, this can be a bit cumbersome, and you can see a lot of, like, files generating. Now, just to give another example, we can see like the upsert use case. So, this is now the current state of the table after the insert. Now, let's say we want to do some upsert. So let's say we ingested some data into our staging table, and we want to, like, do a merge into, right? So what we will assume hypothetically for this particular demonstration is that there is one row in the original table that we are going to update it. And then there is another row that doesn't exist in the original table, but only exists in the staging table. So we are going to just insert the table. And that's what a merge into is basically, right? So after running this particular command statement, we can again see the same kind of flow with the iceberg tree, right? From the data files to the manifest list to the manifest metadata file, and finally to the catalog, right? So, and on the file system, as we can see here, the same thing. Like, now we have two partitions. That's a different thing, because, let's say we had the new record that was inserted in a new partition. So that's why, let's say that's it. But also in the previous partition, you see two data files now, right? That is because we have updated the record, right? We have basically, taken that row and whatever row that matched the particular order ID, and we have updated the record and rewritten that as a new file over here. And we have that new information over here, right? And the inserted one, the record that didn't match that particular original table, it got inserted as a new record over here. And, ultimately, this is how it basically maintains the kind of lineage. And now the latest snapshot is snapshot 2. The latest, the metadata is version 3. As you can see, this updated to version 3 now from version 2. All right. So that's what all the writes were about. Basically, pretty much that's all you need to know about how a write operation works with Iceberg. And now let's take a look at how a select query works, which is a read. And what happens, let's say, for example, a user says, hey, give me the orders from like Jan 26, 2021, right? So going back to the Hive world, just to give an example, just so I remember here, if we had such a statement in the Hive world, Hive would say, well, I'm not partitioned by date, right? But I'm partitioned by R. And the partition would probably be something like 2021/01/26/08, and you'd end up reading the entire table unless you specify that in the statement, which we discuss is a huge problem at scale, right? So what happens with Iceberg is that it basically goes through the same kind of path, right, or the flow of component. And like I said, for reads, the query will start from like the top to the bottom. So we go to the catalog, we get the current metadata pointer. This is the step that you follow. You go to the catalog, you ask for the current metadata file, you get the current metadata file, which is like version 3. And from that, you get the current snapshot, which is snapshot 2. And snapshot 2 contains the location of the manifest list. Manifest list will have all the information regarding the manifest file. And manifest file contains information about partition and stuff, and all those kind of statistical information. And finally, it knows, okay, this is my file. This is what I need to get, and it will return this file to the user. So that's basically the entire key to reading a file in Iceberg, and that's pretty much how it works. So we went through the different CRUD operation and the path Iceberg follows to, let's say, read a file, and now let's say how things look at scale and in production, right? That's super important to know. So to help understand this better, I basically took a case study from Netflix. This study is straight from Ryan's Blue presentation during his time at Netflix, who basically co-created Iceberg with his teammates. So this case study is about a tool called Atlas. So if you look at it, basically it's their time series metrics from their operational system. It's just a month of data and almost 3 million files, as you can see, in like close to 3,000 partition. So the problem here is that they can't process more than just a few days of data. So if you take a look at this particular query, it's a pretty straightforward query, right? You're just trying to get the distinct types within the tags, and then you want to look at a single metric, right? And it's just a weak range of data, as you can see in the dates range here, right? It's not even like a huge chunk of data. It's just a weak range of data. So this should be a pretty straightforward query, right? But with the Hive table format, this particular query took them like close to 10 minutes just to explain the query and not even execute the query. So just getting the files and planning the query takes the majority amount of time. And now with Iceberg, with basic like partition and data filtering, you can see that execution time is only like 13 minutes overall. But the planning time was just 10 seconds. So really from 10 minutes planning time to like 10 seconds, that's a dramatic improvement. But if you do like take a next level step, and if you use like the manifest and like the statistical information from Iceberg metadata and do like min max filtering, you can take this a step forward. And basically what we have now is like the kind of wall time of planning reduced to 42 seconds. Sorry, the execution time reduced to 42 seconds from 13 minutes. As compared to Hive, where only planning took like 10 minutes, and now the entire execution with planning takes 42 seconds, which is a pretty impressive improvement as well. So that's kind of like the real world kind of motivation and like idea behind productionizing like Iceberg and like getting it out there. So hopefully that is kind of like given a high level picture of how things work. But again, reach out to me like for more details around it. And I also have been working on some of the recent use cases with some customers, and we know like what's happening with them. So yeah, it would be interesting to learn more about that as well. So just to end, just to give some design benefits and understand at a high level how we gain value. So obviously you can make efficient, smaller updates. So you can make changes at a file level, and file only get big. So like 128, 256 MB, and you can make changes effectively in Iceberg. Next is the snapshot isolation. So the reads and the writes, they don't interfere in Iceberg. So as you're writing, the reads are unaffected and vice versa. And the writes are atomic, right? Hence, you don't see things like partial writes, concurrent writes. You can usually multiple people, multiple engines can write at the same table, at the same data set, and things like that. It also enables like faster planning and execution. So like for OLAP analytics, I think one of the things is that you write once and read more number of times, right? So Iceberg questions about that. Like, why do we have to collect all the statistics when we're reading, right? Specifically when we know we are gonna read like 1,000 more times than write. So it gives those kind of read side benefits. And it can use, like I said, the statistics to eliminate the non-relevant files. Another part is that we, with Iceberg, we kind of abstract the physical and expose a logical view. So things like hidden partitioning, like I was talking with this transformation column, users don't have to know about the physical layout of the table. It's all logical. So that's really good. And also you have things like compaction. Basically, you are compacting smaller number of files. We know the small file issue in the world of big data, and you don't want to like have a small number of files. So you compact it and make it a bigger file so you can just read it once. And, things like schema evolution is super important as well. And Iceberg supports full schema evolution. So you can change your schema anytime you want. And, you can basically experiment with it. And there is no guarantees, like there are no like loss guarantees in terms of like bringing back zombie data and this kind of stuff. And, that kind of brings us to like, okay, you made some changes like to the table. Can these changes be seen immediately by any engine that you are operating? Yes, the answer to that is yes. Because obviously like the catalog is there and it's open, the data is open, the table format is open. So literally any changes made by any engine can be consumed by any other engine as well at the same time. So there are a lot of new capabilities and features added in the past few years. I know we don't have much time to cover all of that, but at a high level, you should know that these are the basic features that kind of like helps Iceberg make like operationalize Iceberg as a lakehouse table format. So one of them is the expressive SQL. As we would expect with database table, can we do expressive SQL with Iceberg? The answer to that is yes, we can. And that's something important. Things like hidden partitioning I talked about, schema evolution, you can change your schema as you want, and schema changes are independent. So you don't have to like worry about rewriting the entire table in a way which is very cost intensive as well. And you can also do things like time travel. So time travel is super important to like go back to a previous version, analyze that particular data, or even things like version rollback and stuff, right? For example, you have basically, let's say your ingestion job messed up a production table, right? And that table is being used for like a report. So you want to roll back to a previous good state, and Iceberg allows you to natively do that. Just to give an idea of which engines support Iceberg, and just so we can end the talk, again, this is a very comprehensive list, and some of them are like the commonly used engine. But again, there are a lot more adoption happening. And as I'm talking here, like, recently, like a lot of engines have been adding like Iceberg support and, stream processing platforms, a batch processing platform, whatever it is, like, there is a lot of Iceberg support here. But again, like Spark, Fling, Dremio, Trino, Presto, Snowflake also recently added the support. Athena is there. So yeah, so a lot of engines are there who are also Google BigQuery recently added support. So yeah, there are a couple of engines who are recently adding support as we go gain like more access to it. ClickHouse is something that recently added as well. So yeah, okay, controversial side, but not really. So as of today, there are like three data lake table formats, and I can understand you might want to know like how they compare. Uh, but again, this comparison can be at different angles, like feature level, performance, adoption, or community. In this talk, I'm not like going on to this. We don't also have the time to do that. But just that for a future reference, I'm just going to like show some of the features. But again, feature wise, we are going to have these features in each of these table format at some point of time. So it really depends on what the community wants as a feature. So yeah, but here it is like, so you can do a based transaction with all these table formats. Partition evolution is something which is very particular to Iceberg. It really separates Iceberg from the other table formats. So things like I said, with like you don't need to like separate like partition columns. You can easily like evolve your partition and those kind of stuff. You don't have to rewrite tables and things. So that's super important. Schema evolution is available in all of them. Time travel as well. Merge on read is like a kind of like a update or delete technique that is basically like that basically can help you speed up like these updates and deletes, row level updates and deletes. Iceberg has Hoodie has it. Delta recently added, if I'm not wrong. Again, it's a bit limited as of now, but they recently added it. Z-order is a multi-dimension clustering technique to make your queries fast and organize your files in a better way. All of these table format have it. Project Nessie is a catalog, like I was talking about the catalog. It's a catalog, but again, it brings things like Git type semantics. So you can do things like GitHub. Like for example, you can create your own branch. You can do your own kind of isolated analysis, and we can talk more about it later about it. But yeah, so Project Nessie is kind of very native to Iceberg. Enables Git as code, multi-table transaction. Apache Hoodie doesn't have that support, but Delta Lake had that support at some point of time. But I think the recent fork doesn't have that merge. But yeah, we should be able to work that out. But one core component that I always encourage like folks to look at from an open source perspective is also the diversity of the project. So my experience with has been like pretty much like a lot on open source as well. So more diverse a project is, there less chances of bias decision, and that way we can work towards a common community goal. So let's say to make a new feature available. So these are just two representation. Doesn't really mean anything. It's just from OSS Insight. In one of the left one, I'm comparing Iceberg with Delta Lake. All the bubble that you see is basically different companies and individual contributing to the project. So as you can see on Iceberg, we have a couple of bubbles. A lot of bubbles mean that's good. It's diverse. We have people from a lot of organization, Tencent, Netflix, Apple, Dremio, Tabular. They really contribute a lot to Iceberg. With Delta Lake, Databricks is like the kind of the main like contributor, but they also have a couple of other them. And for the Hoodie, again, you see a lot of bubbles. So that means, again, a lot of contributions happening from different sort of people. So yeah, I would highly encourage folks to check out Iceberg project as well, and see if there is anything for you guys to like contribute and also be a part of the discussion, right? It's super important to have that. So having said that, how do we get started with Iceberg? Iceberg, there is the official Iceberg page. You can basically go there and pull up a Docker image. I personally have a Docker image as well. You can basically just pull that out, and you can run your own Iceberg data lakehouse, which is like pretty easy to do that using Spark. Everything is open source, so you don't need to use like a paid engine or something like that. But also within Dremio, we write a lot of blogs and do a lot of things around Iceberg. So you are free to check them out. We also have Iceberg 101 course, which is like a diverse course around everything Iceberg. So that might be a good way to like look at it as well. But thank you so much for the time today, and giving me the scope to like really talk about Iceberg in general, and giving an idea about data lakes and table formats. So thank you so much. Yeah, I'm open to any questions in general. Yeah.
Yeah, thank you so much, Dipankar. It's such a great presentation. So we have still some time left.
Yeah.
Yeah, so we actually have a bunch of questions in the comment
Right.
section. Yeah, if you want to take a look and see if you want to pick a few to answer, I think we got some very diverse
Right. Yeah, and I
question
can.
here.
Yeah, for sure. And I can understand like we can go very diverse because we are dealing with different technologies and stuff here. But I can pick some of them, as the time permits. But again, like I said, you can feel free to reach out to me or like Shinran as well. She has like working knowledge as well. So yeah. Uh, I can take one of it. Like I said, the first question from Nitish: what SQL-based tools can data analysts use to access the data on a lakehouse? So, like I said, the adoption is only increasing. Like if you're using like a P tool, like for example, like even with like tools like for example, like Dremio, like it's a full SQL interface, but there are Trino and like things like for example, like now even with data warehouses, right? They are making it natively available. So I think there are a couple of options. So we also like within like I can talk about like the Sonar compute engine, which is like Dremio's compute engine. They have native integration with like BI tools like Tableau and Power BI or Superset. So all you have to do is basically like create Iceberg table and download a Tableau file, and that's it. You are connected to Tableau, and you can do your analysis directly with the Iceberg table on tools like Tableau and stuff. So that's something super important to know.
Yeah, at Netflix, we actually mostly use Trino on top
Right.
of Iceberg, but for most of the data engineering production job, we actually use Spark on top of
Spark.
Iceberg
Yeah.
table. Yes,
Right.
and
Yeah, for sure.
you can both use SQL to query through them.
Exactly. Yeah, for sure. Yeah.
So, okay, I see this very interesting question, so I'll pick that for you.
Sounds good. Yeah.
Okay, so since Iceberg has a snapshot mechanism, so each write will have one snapshot. So 3 minutes insert will have 3 minutes snapshot. I think this is a super interesting question.
Yeah. It can sound like yeah, that's a very valid question. It can sound like each write is writing a snapshot. So yeah. So the idea is to obviously repurpose the snapshot as well as we can. Like the Iceberg tries to like repurpose it as well. So you would probably not end up with that many snapshot for every write. So I just meant to say that each and every transaction that you make, basically Iceberg tracks it as a snapshot, but there is a concept of reusability as well. So you can also also you can control how many snapshot you can write and those kind of tweakings as well. Whether you're using something like Spark, and or some other engine like Trino, you can use that kind of configuration and basically decide. Also, the idea is that you can obviously have like a lot of snapshot, but you don't need to like have those snapshot. You are obviously it's good to have those snapshot. For example, doing things like time travel and stuff. But you can decide to expire snapshot. So most of the organization that kind of have I have worked with, they will have these regular maintenance strategies where they kind of like run this kind of maintenance stuff. Also, there are tools coming up now which allows you to do like automatic maintenance. So you can basically schedule a job and you can clear up those snapshots as well. But yeah, to your question, the idea would be to repurpose as well. Yeah.
So Dipankar, I remember you also, I think it's a couple of weeks ago, you also post about how Iceberg support auto compaction of manifest file, right? I think
Yes.
that's
Right.
also a related aspect that, hey, if you have, say, a use cases where maybe it's like you are writing Flink real-time job output to
Exactly.
Iceberg, and you might creating a lot of snapshot and also metadata file, and then
Exactly.
that's where that you want to do some compaction so that you don't get into the overhead burden of maintaining all those files existing.
Exactly. That's the whole point of it. And the whole responsibility, like the ability to do compaction is provided by Iceberg, but obviously the responsibility to implement that is on the engine side, the compute engine side. So it depends upon the capabilities. Like for example, Spark is a really feature-rich engine with Iceberg, so you can use that. But again, like there are like tools like within Dremio, I know like we are building up like automatic compaction tools and stuff. So that's also super helpful. I know Tabular is also doing it. Like so, yeah, that's again super interesting to know. I can take one. That's okay.
Yeah, go ahead.
It says, is it more effective for batch type or real time? Yeah. So the whole point, the Iceberg works really good with like even like with batch and streaming. In the past, actually, like we had some issues when like we saw a lot of like Shinran mentioned, like there were a lot of issues. Like for example, like with streaming, you are writing data in batches, right? So that means you're going to end up with a lot of files. But now with the new strategy, which is like I kind of mentioned over the slide, it's called merge and read. You can control that, and basically you can control that kind of like smaller updates. And so that's how you basically effectively use it for real-time use cases. Flink is a really mature, I would say, a real-time engine that is used with Iceberg. But again, there are a lot of platforms coming up in the similar line. So I would say it's again effective for both use cases. We have seen it for both the use cases.
Okay, I see this question. So Anchor asked about will merge into work effectively in case of a streaming application with Apache Iceberg format will upstairs support efficient and fast here.
Yeah, that's what the whole point is. Like I was saying, like going back to my previous question, is kind of related. Like so, with Iceberg now, with like the MOR, the merge on read, the whole point is to like focus on that part and efficiently being able to like do things like merge into. So yeah, so upserts are going to be efficient now, and we have seen it. To be honest, like I was just experimenting with it the other day as well, and we see kind of like those kind of efficiencies built up. But again, realistically, I don't have a pinpoint example to point to like when we saw that kind of like efficiency, but we definitely, that's one of the like whole point of having that kind of like feature at in the first place. So that's the whole idea with like we are going to like make upserts and merge into more efficient with Iceberg. I can choose. Okay, I think it's a basic question as well. I think it can be confusing, so I can take that. How to choose when to go for database or Iceberg? So it can be very generic. Yeah. So I understand, like the whole. So the way I see it is like the databases are basically they have everything piled up together, right? The storage engine is there. There is the compute execution engine, and there is a storage layer and everything. And that's what is pretty much with data warehouses, right? With Iceberg, like the architecture in general, we are kind of like breaking things up, like I said. And remember the image that I kind of initially presented. Ultimately, it's your own like choice to decide what tool to adopt at what point of time. We don't want to restrict people, say, hey, you have to use Iceberg for this specific use case. But situations where Iceberg is a good use case is that you have like a lot of operational systems, you have a large like a data lake environment, you are having hard time managing the tables. So a usual kind of natural move would be to like migrate something to like Iceberg, because that's how you're getting to deal with large petabytes of data. So those are the kind of like aspects in terms of like if you compare, although the comparison is not like very I would say apple to apple, because a database can have a lot of components, and within that component is actually a table format which is very proprietary to the database. With Iceberg, it's kind of the open table format.
Yeah, and I honestly think that's exactly one of the benefits of using like Iceberg and table formats is that you can decouple the table formats from the storage underneath it,
Yes,
and also the query region on top of it, right? Like you can
exactly.
use straight on the query, Spark, or
Yeah,
you can like write data to it from Flink, and then let's say in the future sometime Spark is out and you
yeah.
might use a new different processing framework to query data from Iceberg. So they're
No, for
not
sure.
as coupled together as the old data warehouse type of
Whereas
databases.
exactly, I think that's the whole point with this, and I think that's the whole idea. Like, for example, now we see Iceberg even being used like as a table format for like machine learning feature stores. So feature stores are like really important now in the ML world, specifically when you're feeding real time features, for example, Uber prediction and stuff. So I think that's super important. That's another use case as well.
Okay, maybe we can take one more question, Dipankar. Do you
Mhm.
want to pick one?
Yeah, there are a lot of questions to choose from actually. But yeah, I can let's pick up like if you can explain how to capture CDC using Iceberg. That's a new feature. Satyabrata has that question. Yeah, okay. So yeah, so CDC, we have like the community have been in talk for like a native CDC ability. CDC is important, so we want to like capture the changes as well. So now in the version 1.2.0, which was our last release, actually day before yesterday, it was 1.3.0 release, which again brought like a lot of new features. But again, in the last release, we had the native capability with CDC. So now basically you have a Spark procedure, and you can basically use that Spark procedure to create a table called like changelog view, and you can capture all those changes to the table happening on real time using that particular procedure. So it's a completely new procedure. I haven't really seen much of the use case because it's just released a couple of months back. But yeah, in general, I think that's the whole idea that now natively you can basically run a Spark procedure, and you can capture those changes to the table, and then you can process that, or you can send it to the downstream analytical applications or whatever requires that changes. And there are different options to do that. You can use like a starting of a snapshot ID. For example, let's say you have 10 snapshot and you want to like capture the changes from like 1 to like 8. You can just mention that in that command, and you can just pass it as an argument, and you can basically create that, capture the changes. So that's super helpful now with the native capability.
All right. Well, we're right on time. Well, first of all, thank you, Dipankar, for this amazing presentation,
Of course, thank you
answering
so
any
much for me.
questions.
Yeah.
Yeah, it's super great, and thank you everyone for joining today. And I hope you guys all learned something, and hopefully in the future we'll bring Dipankar again to our event, and we'll talking about something else, and so he can share more of his knowledge with everyone here.
Of course, yeah. All right. Thank you so much, everyone.
Yeah, thank you so much,
Thank you,
everyone.
Shinran. Yeah.
Yep, have a great day and have a good
Bye.
weekend. Bye.
Bye.